Traditional computers are hitting a physical wall. To keep processing power growing, engineers are turning to a resource that travels at the absolute speed limit of the universe light. For decades, we made computers faster by shrinking silicon transistors, but as these gates packed closer, they began generating extreme heat, creating a physical bottleneck for standard chips. Optical computing replaces electrons with photons. Instead of forcing slow electrons through copper wires, this processes direct packets of light through microscopic pathways. Think of traditional computing as bumper-to-bumper rush hour traffic. Electrons crowd together inside narrow copper pathways, rubbing against each other and creating computational friction and heat. Light is different. If you cross two searchlight beams in the night sky, they pass right through each other without colliding. Photons generate zero friction heat and travel at the speed limit of physics. To guide this light, engineers etch microscopic channels onto silicon. These are called silicon waveguides, and they act as the light-based equivalent of copper wires. Imagine a microscopic hallway lined with mirrors. When you shine a laser down it, the light bounces off the walls, following the bends perfectly without leaking out. That is how waveguides route data. This routing relies on total internal reflection. By changing the boundary materials, the light is physically trapped, bouncing along the core channel without losing signal strength. To make decisions, computers use logic gates. Optical computers use optoelectronic logic gates, which act as translators between electrical signals and light waves. Think of a canal with a toll gate. A small electrical signal acts like a gatekeeper, raising or lowering a barrier to control when light wave bolts can pass through. These barriers are light modulators. They slice a continuous laser beam into millions of individual pulses, transforming raw light into binary ones and zeros. Traditional silicon chips suffer from latency. Before a transistor can send a signal, it has to charge up like a tiny battery. This charge time creates tiny, unavoidable delays. This delay is a problem for modern artificial intelligence, which relies on matrix multiplication. These are massive mathematical blocks requiring billions of simple calculations. In an electronic coup, this math is solved sequentially. It is like a line of workers writing answers on clipboards and passing them down the line one by one, waiting for each step to finish. An optical computer solves this instantly. It is like shining a laser through colored glass stencils. The moment the light hits the wall, the blended colors show the answer at the speed of light. Because the calculation happens as the light wave passes through the silicon, there are no capacitors to charge, allowing equations to be solved with zero latency. This brings latency down from nanosecond to sub-picosecond, making optical processing thousands of times faster than traditional silicon chips. Optical processors are also incredibly energy efficient. Because light waves pass through waveguides without electrical resistance, they generate almost no heat, eliminating thermal waste. Traditional data centers are facing an energy crisis, paying an average of $15 per kilowatt-hour just to power massive cooling systems that keep hot silicon chips from melting. Transitioning to optical components cuts these cooling budgets. Because optical chips run cool, data centers can save millions on electricity bills. Upgrading a single server rack to optical components can save up to $378 every year in power and cooling costs, lowering both carbon footprints and utility bills. Optical systems also boost bandwidth using wavelength multiplexing. A single waveguide can carry many different colors of light simultaneously, with each color acting as an independent channel. Imagine splitting a rainbow laser beam into separate colored streams. Each color carries its own stream of data, allowing massive parallel files to travel through the same microscopic channel. When comparing the two, traditional CUS use low hot electrons and copper wires, while optical systems use fast, cool photons and waveguides to calculate math instantly. However, optical computing has challenges. Converting light back into electricity for standard storage creates a bottleneck, limiting the overall speed of the system. Size is another limit. While silicon transistors can shrink to 3 nanometers, optical waveguides are limited by the physical wavelength of light, making them much larger. To solve this, engineers are building hybrid chips. These designs combine the speed of optical channels with the small size and storage capabilities of electronic circuits. In these hybrid systems, electronics handle memory storage and coordination tasks, keeping the computer stable and compatible with current software. Meanwhile, the optical coprocessor takes over heavy calculations, solving complex neural equations at the speed of light to prevent lag. Importantly, these hybrid chips can be built in existing silicon factories, allowing manufacturers to keep costs low and speed up commercial adoption. The roadmap is fast. Over the next decade, these coprocessors will enter commercial data centers, reshaping computing speed and efficiency. By bypassing the physical heat ceilings of electricity, optical computing ensures we can continue scaling up artificial intelligence and cloud networks sustainably. At Laymans Field, we believe that understanding the future of technology shouldn't require a doctorate. We deconstruct the science behind these breakthroughs for everyone. By replacing slow electrons with photons, optical computing is paving a bright path forward. Thank you for watching Laymans Field. We hope to keep bringing knowledge for everyone.